Okay, lecture 28 and the last lecture of our bivariate chapter. So, we're going to finish with a thing called conditional expectation. So, we've got x and y, two random variables, and we're going to define the conditional expectation of a function of x, so g of x, given that y equals y, is going to be in the discrete case, we're going to sum over all values of x, our function g of x, times the conditional probability of x given y. In the continuous case, we're now going to integrate over the real number line, minus infinity to infinity, our function again, g of x, times by our, well actually, that's not quite right, that should be our f of x given y, so our PDF with respect to x. So when we're doing this, when we work out expectation, it's all about x. X is the random variable in this case once we've conditioned on y equaling y. So let's do an example. We've got our probability density function. It's a half, and basically x lies between 0 and y lies between x and 2, and they both lie between 0 and 2, and it's 0 otherwise. We want to work out what the expected value of x is given y equals 1.5. Well, we're going to have to build this up slowly. So let's start by, first of all, we're going to work out the marginal distribution of y. So how do we do that? We are going to basically marginalize out x. So we write down our bivariate probability density function, and we know that x goes from 0 to y. So that is x over 2 from 0 to y. So that is going to give us y over 2 for y lies between 0 and 2. What about our conditional distribution? So we want the condition of x given y. Well, that is going to be f of x, y, given our marginal of y. Well, that is just equal to a half over y on 2, which equals 1 over y. We've just got to be careful because for this to be a valid probability density function, we're going to need that our x lies between 0 and y. Because the thing to remember about that conditional distribution is that's basically a constant, that 1 over y. I know it looks like it's a function of y. It's not. It's a function of x given y. So it's constant in terms of x. So now we can put that together and we can work out the expected value of x given y equals y. So what we're going to do, we are going to, this is a function of x, so we're going to integrate over x. We're going to write our function, which is x, and our PDF, which is 1 over y. And the values of x goes from 0 to, let me just check that, x goes from 0 to y. So just remember this is a constant term. This is 1 over y, x squared over 2, so x goes from 0 to y, which is 1 over y, y squared over 2, which is basically y over 2. So expected value of x given y equals y is y on 2. So now we can calculate the expected value of x given y equals 1.5. It's going to be 1.5, we just substitute in over 2, which is 3/4. Okay. That we don't use very much, but we do use this next theorem a lot. It's a beautiful thing, and it actually ends up to be Gary-Glonick trick number 6, which is often you can simplify expectation by conditioning on another variable. So let's look at this. We're saying x and y are random variables, and then the expected value of x can be written as the expected value in terms of y of the expected value of x given y. So sometimes we can make a problem simpler when we've got a difficult expectation by conditioning on another variable, and then things can drop out. You'll see this appears quite a lot. So to give you an understanding of what we're doing here, let's actually look at the proof, and we'll look at the proof in the discrete case because I think it's the easier one to look at. So let's start by writing down the expected value of x. Well, that by definition is we're going to go over all values of x times the probability that x equals x. That's our definition of expectation. But now I'm going to use the law of total probability. So this is x. I could now go over all values of y. So I've got my x there. And we can rewrite the probability x equals x as the probability that x equals x and y equals y. So what I've done is I have gone from this to this using the law of total probability. Right, we can rewrite that. That's x, that's y, we've got a little x there, and this is the probability that x equals x given y equals y times the probability that y equals y, just by using our multiplication rule. Next thing I'm going to notice is this x here is constant with respect to this y, so it can come inside. So now I've got equals x, y, x, the probability that x equals x, given y equals y, the probability that y equals y. And because this is sufficiently nice, what I'm going to do next is I'm just going to interchange these summations. So this can be written as summation of y, summation of x, the probability that x equals x, given y equals y, the probability y equals y. Looking good. Now, I want you to have a look at this term here. This is the summation all over x of x times the probability x equals x given the probability y equals y. That is by definition our conditional expectation. So we've got the summation of y, and I can rewrite this whole thing as x given y equals y. If you go back to the first slide, that's what that is defined as. And finally we've got our probability y equals y. But what we've got here, this is just a function in terms of y. So I'm summing over all values of y, a function of y times the probability y equals y. Well, by definition, that is the expected value of that thing. So this is the expected value, remember, with respect to y, of the expected value of x given y. And that's it. Okay. We can do a similar thing. I'm not going to do the proof because it's just a bit more complicated, but we've got x and y are random variables. Then we can get the marginal variance of x, so the variance of x. It can be written as the expected value of the variance of x given y plus the variance of the expected value of x given y. So in both cases, we've introduced this extra y. And the first time we do expected of variance, and the second time we do variance of expected, we just interchange them. So that all seems good, but it's a bit of a sense of, well, I don't know how to use this. So we've got this nice motivating example right from the start that we're now going to use. And we use it a lot in what we call hierarchical models. And here's a classic example. We've got the number of eggs an insect lays follows a Poisson distribution with rate of 15 eggs per insect. Fine. The The probability of each one of the eggs hatching is 0.001 independent of the other eggs. So what we've got is once you've got your number of eggs, then you've just got a binomial. So we've got this hierarchical. We've got a binomial, which is the number of eggs that hatch, that has got a fixed number of trials and a probability of 0.001. But the fixed number of trials is also another random variable, which is why we call this hierarchical, that you have parameters in one random variable that is also a random variable. So we'll call a hierarchical model. So what we're going to do now is we're going to actually work this out using these conditional expectations. So first of all, let's get some notation. To be consistent with what I've done before, we'll say we'll let y be the number of eggs laid by the insect. So we know that y is Poisson with a mean of 15. X is the number of eggs that hatch. So we know that x, given we've been given the value of y, is going to be binomial. Fixed number of trials is y, and our probability is 0.001. So you can see that, as I said, x is a binomial random variable, but one of its parameters, in this case what we'd normally call n, which is our fixed number of trials, is y. It's another random variable. So how would you get the expected value of x? Now, you could do like we did in an assignment earlier, where you could actually work out the distribution of x and do it that way. But because we've got this nice conditional expectation, it's also called a tower property, but we normally in this call conditional expectation. I can do this really quickly. I can say this is equal to the expected value of x given y. Let's just look at this one here. Let's assume we had a fixed value of y. What would be the expected value in a binomial? It would just be n times p. So in our case, it's going to be y times p. So we can write this as the expected value of, I'll put it as 0.001 y. By the fact that we've just got a constant here, we can take that constant and bring it out the front. So that's 0.001, the expected value of y. But y is just a Poisson random variable, so we know the expected value is 15. So that's 0.015. Check, yeah. What about the variance? Well, the variance of x is going to be the expected value of the variance of x given y plus the variance of the expected value of x given y. Well, again, if we look at this, this is saying if I gave you a fixed value of y, how would you work out the expected value of a binomial? It would be np1 minus p. So putting that together, that would be the expected value of 0.001 times by 1 minus that, which is 0.999 times by y, plus the variance. Well, we've already worked out the expected value of x given y. That is just 0.001 y. Remember, these expectation and these variances are all about y now. So we can bring out our constants. We've got our 0.001 times by 0.999. We want the expected value of y. Plus with variance, that constant, you can bring out the front and square it. So that's 0.001 squared. Variance of y. And the expected value of y, well, y is a Poisson random variable, so its expected value is 15. Again, y is a Poisson random variable, so its variance is also 15. So we've got 0.001 times by 0.999 times 15 plus 0.001 squared times by 15. And if you do that, I got 0.015. Very nice. So again, this nice thing is you don't have to get the distribution if you don't need to. If you just want expected value and variances, you can use this, what we call conditional expectation, conditional variances to get that. So that's it. Next time we'll have a bit of a case study using some bivariate stuff, and then the next chapter we start looking at what we call discrete time Markov chains. Okay, see you next time.